Welcome to Electrical Lad, your trusted source for simplifying electrical, hydraulic, and pneumatic concepts in a clear and practical way. Remember, hydraulic systems can operate at extremely high pressures and can cause serious injury or equipment damage if handled improperly. Always ensure you are properly trained and follow all applicable safety procedures before working on any hydraulic system. I still remember the very first time I looked at a hydraulic schematic. I unfolded the drawing, looked at all the lines, boxes, arrows, springs, and strange symbols, and honestly, I had no idea what I was looking at. It looked more like a subway map than a machine. I thought, there's no way I'm ever going to understand this. But after working with hydraulic systems for years, I realized something. The problem wasn't that hydraulic schematics are difficult. The problem was that nobody explained how to read them. In this video, I'm going to show you the same three-step method I use whenever I read a hydraulic schematic. First, we'll identify the major components that almost every hydraulic circuit has. Then we'll learn how to follow the path of the oil through the system. Next, we'll take the mystery out of directional control valves so they finally make sense. And finally, we'll put everything together by reading an entire hydraulic circuit from start to finish. By the end of this video, you'll have a simple system you can use to read almost any basic hydraulic schematic. Before we get started, it's a good idea to familiarize yourself with the basic hydraulic symbols you'll see in this video. To help you follow along, I've included a downloadable hydraulic symbol reference in the description below. Whenever I receive a hydraulic drawing, I never start by looking at all the symbols. Instead, I ask myself one simple question. What are the major components? Almost every hydraulic circuit contains the same basic building blocks. First, find the reservoir or tank. Think of the tank as home. Every drop of hydraulic oil begins here and eventually returns here. Next, find the hydraulic pump. The pump draws oil from the tank and pushes it into the system. Here's something important that many beginners misunderstand. The pump creates flow. It does not create pressure. Pressure only develops when the oil meets resistance. That's one of the most important concepts in hydraulics. After the pump, look for the pressure relief valve. This valve protects the entire hydraulic system. If pressure becomes too high, the relief valve opens and safely sends oil back to the tank. Without it, hoses could burst, fittings could fail, or the pump itself could be damaged. Sometimes a hydraulic system includes a secondary relief valve. Its purpose is to act as a backup safety device in the event the primary relief valve fails or cannot relieve pressure properly. Under normal operating conditions, the secondary relief valve remains closed. It is typically set 10 to 20% higher than the primary relief valve, so it only opens if the primary valve fails to protect the system from excessive pressure. Next, locate the directional control valves. These are the traffic controllers of the hydraulic system. Their job is to decide where the oil goes. I will explain later how they do that. Finally, find the actuators. In most beginner schematics, this will be a double-acting hydraulic cylinder. Now you've identified the 5 components that make up most basic hydraulic circuits: tank, pump, relief valve, directional valve, and the cylinder. Once you know where these components are, the schematic already looks much less intimidating. Now that we've found the major components, let's do something that makes every schematic easier to understand. Instead of looking at symbols, let's follow the oil. Most hydraulic schematics show valves in their normal, de-energized position. When analyzing or troubleshooting the system, assume the pump is running and oil is flowing. Now let's follow the flow through the circuit. The pressure lines are shown in red, while the suction and return lines are shown in green. With the valves in their normal, unenergized position, the cylinder ports are blocked. Since the pump is running, pressure rises until the relief valve opens, sending the oil back to the tank. In this example, the relief valve is set to 1000 psi. Now let's look at directional valves. At first glance, directional control valves can look complicated, but they become much easier once you understand how to read them. Each box in the symbol represents one position of the valve. So, a valve with 3 boxes has 3 possible positions, and the lines inside each box show the path the oil can take in that position. The main ports are P, T, A, and B. P is connected to the pump and supplies pressure oil. T is the return path to the tank, and A and B connect to the two sides of the cylinder. If pressure flows from P to A, the cylinder moves in one direction. If it flows from P to B, the cylinder moves in the opposite direction. You don't need to memorize every valve symbol. Just ask two questions. Where is the pressure oil going? And where is the return oil coming from? Now let's read circuit 1. Now let's assume the pump is running and oil is flowing, but the directional control valve is in its center position. Since the cylinder ports are blocked, the pump has nowhere else to send the oil. The relief valve therefore opens and diverts the flow back to the tank, limiting system pressure to 1000 psi. Now, when the directional control valve shifts to the extend position, the flow path changes. The pump's pressure port, P, is connected to port A, sending pressurized oil to the cap end of the cylinder. At the same time, port B is connected to the tank, allowing oil from the rod end of the cylinder to return to the reservoir. With pressure on one side of the piston and the other side connected to the tank, the cylinder extends. Once the cylinder has fully extended, we can de-energize the solenoid. The spring returns the directional control valve to its centered, block position, blocking the flow paths to both sides of the cylinder. With both cylinder ports blocked, the cylinder remains extended and holds its position. To retract the cylinder, we energize the opposite solenoid, shifting the valve in the other direction. The valve now connects the pump's pressure port, P, to the rod end of the cylinder, while the cap end is connected to the tank. Pressure oil pushes against the rod side of the piston, while oil from the cap end returns to the reservoir, causing the cylinder to retract. Now that we understand the basic operation of the circuit, let's take a closer look at some of the additional components shown in the schematic and understand the role each one plays in the system. First, let's talk about directional flow control. A directional flow control valve is used to control the speed of an actuator by regulating the flow of oil in one direction. This allows us to adjust the extension and retraction speed of the cylinder independently. Inside the valve, there is a built-in check valve. In one direction, the check valve closes and forces the oil to pass through the adjustable flow control orifice, allowing us to control the cylinder's speed. Figure A. When the oil flow reverses direction, the check valve opens and allows the oil to flow freely through the valve with very little restriction. Figure B. Next in our circuit is the hydraulic accumulator. An accumulator stores hydraulic energy and can serve several important functions. In this circuit, it can help absorb sudden pressure spikes and reduce hydraulic shock or pressure surges. It can also provide a temporary supply of pressurized oil if there is a sudden drop in system pressure or a short interruption in pump flow. For safety, the accumulator must be depressurized when the system is shut down. When power is off, the valve connects the accumulator to the tank, allowing the stored pressure to safely discharge. To pressurize the accumulator, the manual valve is turned to block the path to the tank, allowing pressure to build up. Now let's analyze the circuit. The main difference between Circuit 1 and Circuit 2 is the type of load being moved by the actuator. In Circuit 2, the actuator is moving an overhung load. The directional control valve in Circuit 2 is the same as the one in Circuit 1, a four-way, three-position valve with a blocked center. So, the basic operation of the circuit is the same. However, because this circuit is controlling an overhung load, we need to add another valve to ensure proper operation and improve safety. This is a counterbalance valve. It is commonly used to prevent an overhung load from running away or free-falling when the directional valve is shifted. A counterbalance valve provides controlled resistance to the overhung load and keeps the cylinder under control. A simple flow control valve is not always suitable for this application. Restricting the flow leaving the cylinder can create excessive pressure on the rod side, potentially causing cylinder damage or failure. The counterbalance valve is designed to control the load safely while preventing this excessive pressure buildup. If you want to learn more about counterbalance valves, check out my video, Hydraulic Loads Dropping. Counterbalance valves finally explained. I explain how these valves work and why they are so important when controlling overhung loads. The next time someone hands you a hydraulic schematic, don't try to understand the entire drawing all at once. Start with these 4 steps. First, identify the major components. Second, follow the oil through the system. Third, understand what the directional valve is doing. And finally, read the complete path from the tank to the actuator and back again. Once you stop looking at a hydraulic schematic as a collection of symbols and start seeing it as the journey of the oil, everything becomes much easier. If you found this video helpful, give it a thumbs up and consider subscribing to Electrical Lat. I make videos that simplify hydraulics, electrical systems, PLCs, and industrial automation, so you can understand how real machines work, not just memorize theory. Thanks for watching, and I'll see you in the next video.